It's a pleasure to introduce Matthew Ballard from University of South Carolina, and he's going to be speaking about generation in characteristic.
Thank you, Ernesto. I deeply appreciate the opportunity to speak. I really wish I could be there, but as Will Smith said, my life's been smack flipped upside down. So. And with that out of the way, what I want to talk about today is sort of a basic question in derived categories, and one that has received a good deal of interest over the past decade or so. Okay. Right. So let me say that parts are joint with Alexander Duncan, who is here at South Carolina, and Patrick McFaddin, who is at Fordham, and with Pat Lank, who is also at South Carolina. Okay. And what I want to do is basically figure out if we have a really simple generator for derived categories of coherent sheaves for varieties and characteristic P. Okay, as we know, the algebraic geometry over non-zero characteristic is very closely bound to the structure of the Frobenius map. Right, so let me just recall that real quickly. I'm sure everyone is familiar with it, but perhaps some conventions might intervene. So I'll denote the Frobenius map by F, right? It's just the map that R goes to R to the P, and here R is going to be over a field K of characteristic P. Of course, I'm going to take P bigger than 0 for most of the time. Okay, and then also globally, I'll just use F to denote X. And then if I have some positive integer, FE will just be the composition E times for the Frobenius map. Okay. So one of the most fundamental results in understanding how the behavior of the Frobenius morphism affects the homological properties of the variety or the ring is Kuhn's theorem. What that says, it says, okay, so we start with a Noetherian ring. And it gives an equivalent characterization for regularity of the ring. So R is regular if and only if the module, well, it's still R itself, but viewed via the Frobenius action, is flat. So I'm interested in bounded derived categories of coherent sheaves. I want finally generated things. So let's make a definition, well-known definition. We say R is F finite if this guy is finally generated. Okay. And there's a amplification of Kuhn's theorem. So this is due to Rodizio. So if we go say R is Noetherian and F finite, then R is regular if and only if F lower star R is perfect. Okay, so it has a finite projective dimension. So me, when I study derived categories, I see a statement like this. What my first thought is well, I have another condition, which allows me to detect regularity, right? So we also know that if this inclusion of perfect complexes inside the derived category, the bounded derived category of finally generated R modules, is an equivalent. Let's say it like this. This is also equivalent to R being regular. Okay. So is there some notion that might unify these two things, right? So we see that this Frobenius push forward is very good at least detecting regularity of the ring. Is there some statement we can make about generation via the Frobenius push forward? Okay. And sure enough, there is. So first theorem here, due to myself and Pat Lank. So R is going to be, well, I'm not going to say Noetherian because there's some details, but they aren't really. They're just some details, but for safety's sake right now, but we'll say this. So let's just take R to be finite type over our field K of characteristic P. Okay. So then there exists some E such that some iterate pushing forward the structure sheaf some number of times generates the bounded derived category of modules. Okay, so let's just remind ourselves. All right, we say as a subcategory generates if the smallest fixed subcategory, meaning closed under direct sums, and triangulated. So maybe I should say triangulated here. If the smallest fixed subcategory containing S is T itself. Okay, so basically every object can be achieved by just taking some number of cones and some summands, or taking some summands and some cones. Okay, and shifts and sums and things like that. Okay. So, so why is this nice? Well, so let's just note. So in general, R is about the nicest object you can pull out from the derived category if you reach your hand in, but it's not ever going to be a generator if you're not a regular ring. All right, so pushing forward by Frobenius converts it to a generator. So in this sense, maybe this is really a note. This is more opinion. So this is some type of simple generator that we can understand. So most of the constructions of generators for bounded derived categories in the singular case are built as some sums of pieces that come from pushing forward inductively lower dimensional generators along particularly chosen subschemes of R, of spec R. Okay, so corollary is that in the sense it's simpler, it's nicer. So if we assume if R is normal, then in fact we could say there exists reflexive module generating the bounded derived category. That reflexive module being this iterated push forward. Okay. So you're not going to get a vector bundle, but, and you know, if you're not Cole-Macaulay or something, you're not going to get a maximal Cole-Macaulay ring. So reflexive is a pretty good. Well, I don't know what else you would substitute in there that would be plausible, but it's a pretty good substitute for a vector bundle. Okay. And so some examples, right? So of course, if R is regular to begin with, then right. And this is just a projective. So so we generate. I can get back a copy of R by just you know, tensoring with the dual and looking at the evaluation map or something like this. Okay. Okay. What's about the simplest singular ring we can talk about? Well, we can talk about the ring of dual numbers. Okay. And if we look at Frobenius push forward, well, as abelian groups, that's just the same thing still. The only difference is how does X act? So if I take X and act on R here, well, that's X to the P. I guess let's put an E up here, P times R. Okay, and well, if you know PE is bigger than or equal to 2, then this is 0. Okay, so this is isomorphic, just 2 copies of the residue field for this local ring, and it's well known that K generates the bounded derived category of the ring of dual numbers. Okay, and so the general proof of this is not too far from what I've shown you, but I have some other things I want to cover, and I will circle back to this if time allows. Okay. All right, so that's the local case, but really the argument works globally if you interpret it correctly. And so X now is a scheme of finite type over K and separated. Maybe quasi-separated, I don't know. And F finite, I said that up here, right? Ah, right, F finite up here, because I do want this to be an object of a finally generated thing. Okay, and so then if I take the push forward of the perfect complexes, some iterated push forward, then this generates the bounded derived category coherent sheaves on X. Okay, and as I said, this we want to relax this in the theory, and it's there's some details there, but I don't think it's there's some details, there's some ideas, they just have to be written out completely. Okay, so one nice thing to say about this, right, is it's usually pretty easy to construct generators of the perfect category, right? Take some ample line bundle and take a sufficient amount of powers for it, right? You're not going to get all the complexes with some singular support this way, but you can get all perfect complexes this way. But if you just apply Frobenius, then in fact you can get all objects of the derived category. Okay, so let's say corollary, right? Let's say X is projective, and same assumptions as above. Now we add X is projective. Let's say L is ample. Then if you take, this is just writing down explicitly what I said before. If you take some collection of sums of sufficient twists of L, sufficient powers of L, then you'll generate the boundary derived category coherent sheaves on X. Okay. So that perhaps is not the immediate translation of what we would think from coming back up and looking at the local case. Where'd it go? Where did it go? Right here, right? You could imagine that, right? You can imagine I just try and just do the direct translation. I replace R with the structure sheet. So when does an iterated push forward of O of X under Frobenius generate boundary derived category coherent sheaves? And now you should note that this is a meaningful question, even if we're smooth now. Right? So this is interesting, even if X is smooth. Right, because we're taking O of X, which almost never is a generator, and we're doing something to it and hoping we produce a generator. Okay, so what evidence do we have for and against such a thing? Okay. So one piece of evidence, well, you can decide whether it's for or against. Let's say C is a smooth curve. And let's say the genus is greater than 0. Or sorry, let's break it down case by case. So do cases on the genus of this over the separable closure. Okay, so genus 0. Well, one can compute exactly what this push forward is. You're going to get one copy of O. I guess I shouldn't use an X here. And P minus 1 copies of the hyperplane bundle. Okay. So indeed, we generate, because we can reduce generation to a question of, we can reduce the question to something happening over K bar. Okay. And now if the genus is bigger than 0, we have one of two things. Either the genus of C is 1, and the Frobenius push forward of O, if I do any power of it, it's going to be a sum. I don't know. I can't see any comments, so should probably check them periodically. Just over the torsion, the PE torsion on the curve, and the elliptic curve itself. I'm getting a minus sign now. Okay. So we don't generate here. And the other thing is if, the other one is or. This is a stable vector bundle on C. Okay, in that case, we don't generate either. So it's perhaps I don't know how you should feel about this. It does seem like more of the usual, where you have a break along, you know, the Clavier case, and things behave well before it and badly afterwards. But I don't know. So at least it tells us that can happen, right? And it tells us it also can't happen, which answers some questions, some obvious first questions. All right, so we're going to say X is F thick if we actually answer this question affirmatively. So if this push forward generates for some positive E. Okay. Now, beyond the case of curves, where do we know something or don't know something? Well, let's do what we know something. So all right, so the first one I mentioned was P1, so projective space. This is okay. I forgot what the multiplicity of the summands are, but let's say this looks like O plus O minus 1 to something, O minus N to something. So it just returns the usual Bielenson collection we like. Quadrics, and this was originally, I think, Langer, and it was reworked by some people. And I think this is okay. In general, people got really excited about a related question, which is, you know, when is this guy a tilting generator? About 15 or so years ago, 10 or so years ago. And that's what Langer actually did, is he classified primes, powers of the prime, and dimensions for each of those, where you actually had a tilting generator given by iterated push forward for Frobenius. So he didn't couch it in terms of generation, but we can work it out from his calculations. Okay. Some rational surfaces. Oops, I said smooth. I meant some. So a very interesting and difficult question that goes along with this is to classify the irreducible summands, the indecomposable summands we get from iterated push forward for Frobenius, up to isomorphism, of course. And that gets, forget whose work it was for this. I think it was blown up in 3 or so points. And it wasn't sort of obvious stuff. It was fairly intricate. coherent sheaves or vector bundles you get from this. Okay, and sort of the big source that follows from some serious machinery is homogeneous spaces. So here, G is semi-simple over K. P is a parabolic. And this heavily uses the result of Bezrukavnikov, Markovich, and Minier. And it was thought about in this language by Samokin. And so the story here is interesting and related. I'm not going to talk too much about it other than this comment. So if you push something forward via Frobenius, you can equip it with a natural structure of a D module, in this case, particular type of one. And what was shown here was D affinity. So that if you just take global sections or maps from O as a D module to any other ones, that captures all the information of the category D modules on such spaces. Okay. So in particular, you're going to capture all the information about any Frobenius push forward in addition to some other stuff. Okay. So, and of course, this subsumes some other examples we've already seen. But in terms of known cases, it kind of begs the question, right? We can look at the obvious question for something global. So say X smooth and projective, and then X is F thick, if and only if X admits a full exceptional collection. Because this is, if you stare at this list and you've thought about derived categories a bit, that would be what you're naturally led to. Okay, so it's I don't know the answer to this, but I will say that, so in general, the summands of this are not full exceptional collection. There's just too many of them as you get bigger and bigger, even if you just think the pieces up to isomorphism. And we also know the examples where we definitely do not have full exceptional collections of line bundles, and we will see here that's a natural place to start poking at this question. All right. So what we can ask is, you know, what was missing from this list up above here was, if we're thinking about varieties with full exceptional collections, or toric varieties. So our toric varieties, F thick. Okay, and so so one thing to note is that, you know, the map that takes, if I have just a polynomial ring in n indeterminates, right? Okay, so this is my Frobenius map, right? But of course, I can basically stick in any integer there and still have a well-defined homomorphism. And if I, you know, do the usual thing of base changing so that it becomes k-linear, this makes sense as a algebra homomorphism. for any k and any m. Okay, so sometimes this is called toric Frobenius. Because, well, you know, when are you going to have covers that are honest affine spaces in of themselves and the maps between them? You know, go affine to affine, preserve this presentation like that. You're going to be a toric variety. And so Vondel and Oberwolfach, I think back in 2006-ish, made a comment. He was interested in mirror symmetry. He was working with Weidong Luan on trying to understand mirror symmetry for toric varieties. And they had this method for going between coherent sheaves on a toric variety and Lagrangians on the mirror real torus, where it used basically the Frobenius map. And so what Vondel said was, well, he was again interested in the case where you don't have any X mainly, because those are a little easier to compute and deal with. But he said that, so toric Frobenius generates dv co X for it. Here, maybe if I say this word split and you don't, confuses you, don't worry, pretend you didn't hear it, for a split toric variety. Okay. So it was like a one-line comment, and then, you know, the paper went on to analyze some final threefolds to look for things where you actually got a full exceptional collection from the Frobenius push forward, iterated Frobenius push forward. And then people tried to prove it, and it became Vondel's conjecture. And there were results. So for stacky surfaces, stacky toric surfaces, Okawa and Uehara proved it. And then for toric final threefolds, Uehara proved it. And then for some toric final fourfolds, probably Nyack demonstrated it. Okay. But that was the end of the story, I think. Became perhaps less interesting, I don't know, over time. But it turns out it's true in general. So, Theorem, me, Alex, and Patrick McFaddin. So it says that simplicial toric varieties are F-thick. Okay. Really, more generally, you can say toric DM stacks with simplicial coarse spaces, if you want. Okay. And so nice things about this, right? So nice things about this is that, well, one, there's no projectivity built in to the statement here, right? So of course, there exist non-projective, smooth, complete toric varieties, where this result still holds. Okay. And then two, due to work of Efimov and others, we know that we can't have full exceptional collections of line bundles in general. In dimension 2, if we're not Fano, and then dimension 3 if we are, or dimension higher if we're not Fano, even. So in general, we can say, and in general, the summands, I'll say this here in a second, but the summands are going to be line bundles for the toric case. In general, the summands of this push forward are not a full exceptional collection. Okay, so well, it's a situation where we already have a full exceptional collection, sure, but there's no easy translation from the summands we get in toric Frobenius to some exceptional collection. It'd be nice if there were, because in some ways this thing is more canonical, right? There's no choices involved. It's just you got characteristic P, you got your structure sheaf, start pushing it forward. Okay. So let me say a little bit about what this looks like in the toric case, and it touches on some things that have been of pretty decent interest, although maybe not the results in that paper that's such interest. All right, so first thing to say is that this guy here really only depends on X up to codimension less than or equal to 1. Let's make that precise. All right, we have a short exact sequence. The usual short exact sequence. Right. That relates the T invariant, the torus invariant divisors, the Picard group, and characters of the torus. So let's base change that to, okay, let's give this a name. Let's base change things to R. And so lemma, and I forget who wrote this down first. I know Uehara featured it pretty significantly in looking at stuff, but if I look at the Frobenius push forward, it breaks up into a sum of divisors in some subset D. They're structure sheaves with some indices. I don't care so much about the multiplicities, but you can compute these. It's not an intractable problem. But where ZH is the integral points of this half open cube. Okay, so S is the rank of number of torus invariant divisors, and you figure out, okay, well, what line bundles can I make on my variety by doing linear combinations of torus invariant divisors, but I'm only allowed to use basically rational coefficients that are strictly less than 1 to get those. Okay. So let's see, we saw P1 before, so let's just see P1 again, because it's a nice simple example. All right, so we have Z, we have Z2, we have Z. This is just a map that takes the class of the two torus invariant hyperplanes to the same line bundle. Okay, so we tensor it with R. right? And so we're going to look at phi of this half open square, and we're going to end up with half open interval of length 2, and I intersect that with z. I get back what we saw before. Okay. And then Pn is just z to the n with here. Okay. So the summands we get, the line bundles we get, don't depend on any of the birational geometry beyond. They don't care about codimension 2 or below. Just these collections of line bundles for anything. Already a hint that we're gonna have some redundancy in general, right? Let's see, what else do I want to say? So there's sort of two approaches to the proof. One, which is the original approach, mainly due to Alex. So this is some combinatorial linear algebra. And the other one is to use the very well known, but sort of lesser sibling of the work of Spanko-Vandenberg on non-commutative resolutions, non-commutative Kreppel resolutions for invariant rings. But this is the non-quasi-symmetric result. So they have a result that holds in general. It is not as sharp as the one in the quasi-symmetric case, but the ideas it uses are sufficient to understand this. Okay. And so, you can, if you take the advantages of 2 is that, hello? No, okay. The advantage of 2 over 1 is that this is easy to understand because they already did it, or at least they already did their arguments for the case where we don't have a torus, but we have a linear algebraic group. And at least you can do this. So if I work in characteristic P, unfortunately, the collection of representations of G don't behave as well as if I'm in characteristic 0. But you can, as I said, the nice thing in this situation is that all the summands are actually defined over Z, so you can make sense of this object as an object if you base change to Q, and and then you can think about things there. And if you do that for quotients by linear algebraic groups, not necessarily geometric invariant theory quotients, but things very close to them that may not give out projective things, then you can get this generation. So the case of the quasi-symmetric case was already covered by Sam and Helper and Meissner as part of their work, understanding in these methods in this geometric case. Okay. Let's see how much time I don't give up. So that's good. It kind of aligns with our expectations about the relationship between these two. I don't know if these are reasonable expectations. I don't know if they're good expectations. They're just expectations born of knowledge accumulated over time. But, does answer the question about torque for Frobenius generating. Okay. And then, another Another result, another thing that it's useful to think about when we think about derived categories is, so how does, right, I kind of know it works for projective space. If I can understand how it behaves under passing to hypersurfaces, right, then I'm in pretty good shape if I have some concrete control over this. So how does this behave under passing to a hypersurface? Okay, in particular for projective hypersurfaces. Okay. So this is another result here that, again, aligns nicely with what we see in life when thinking about derived categories. So if X inside Pn is, I'm going to say generic, so this isn't a completely precise statement at the moment. Hypersurface of degree d less than or equal to n. Then for big enough E, you can write out this push forward. You can break off some ends that give you the components you usually see in these very well-known semi-orthogonal decompositions of hypersurfaces. Orloff and Kuznetsov. So another way to say this is this respects the usual SODs for hypersurfaces, for projective hypersurfaces. Yeah, hypersurfaces in P. Okay. And so there's a whole industry thinking about when does R split off from an iterated Frobenius push forward? When does the structure sheaf, if we're non-affine, split off from an iterated Frobenius push forward? And one of the most useful tools in that is something called Fredder's criteria, which allows us to get our hands explicitly on that question. And this kind of follows from some slightly generalized Fredder's criteria. Okay, and then of course, you can have complete intersections of total degree D. Again, like I said, there's this quote in here about genericity. So there's some detail. This is more serious details to be worked out because I put a quote in there, but yeah, but some statement should exist for complete intersections. Okay, and so let's see. Let me just stop there. I've got about 15 minutes. And if there are questions, then we can use the other time for questions. Say thank you.
Thank you very much, Matt. Questions? Well, thank you very much, Matt, for such a nice talk.
My pleasure. Thank you. Thank you for the invitation. I wish I could be there in person.